Hello and welcome to the Unit 1 full review guide for the AP Calculus AB/BC exam. So Unit 1 is limits and continuity, and it goes from 1.1 to 1.16. On the AP exam, it is 10 to 12% of AB and 4 to 7% of BC. So starting off with topic 1.1, introducing calculus. So calculus is the study of dynamic change, and it uses limits to model this dynamic change. Now you need to know the average rate of change formula, which is your change in y over change in x. And that means that if your change in x is 0, so your x doesn't change, and yet your y changes by some non-zero amount, we know that the rate of change has to be undefined. Really, only two important things here you need to know. Mainly an idea and a glimpse into calculus. So if we look at these two functions here, for our blue one, we're going to have y is equal to 2x minus 3. But for our red one, x is equal to 2. Since our change in y can be any number and yet our x doesn't change, um, it would be like dividing by 0. So really, we say that the rate of change doesn't exist. And in calculus, when we move on to derivatives and we want to talk about instantaneous rate of change, we have to consider average rate of change. And it's very important that you have a very good understanding of average rate of change, but that'll come back in Unit 2. So 1.2, defining limits and using limit notation. The definition of limit can be set as follows. Given a function, the limit of f of x as x approaches c is a real number L if f of x can be made arbitrarily close to L by taking x sufficiently close to c. Okay, that's kind of big, wordy. Can we break it down? It's basically saying if we have a function, the limit as x approaches c, so as x approaches c, the limit of f of x is a real number. If and only if this is the definition, our f of x can be made arbitrarily close to L. So we can pick any distance from f of x to L as long as we take an x sufficiently close to C. Um, Maybe in your calculus class, you may have learned the epsilon delta definition of the limit, but as you'll see here, that is not assessed on the AP exam. It is excluded. For the purposes of the AP exam, you don't have to know it. Now, the common notation is as follows, and we read it as there are lots of ways to read it actually, but I'm just going to read it out like this. The limit of f of x as x approaches c is equal to L, or the limit as x approaches c f of x is equal to L, right? X goes to, you have a lot of different ways to do it, but as long as you understand the notation, which is the most important part, we have a limit and x approaches c on the bottom, and of f of x, and all of that is equal to L. Topic 1.3 starts with estimating limit values from graphs. One key thing here to know is that if we have to be careful with graphs, as if we pick a window zoom that's not how do you say good enough, right? If we don't pick a um an adequate window zoom, you'll notice that the graph can deceive us. So in the top, we have f of x is the absolute value of x over x. And it's very important to notice it's very hard to tell the limit as x approaches 0. It looks like maybe it's 0, like I don't know, like it exists, but in reality, if we look at the better zoom, we'll see something, but we'll come back to that. Now, if we consider x squared, what is the limit as x approaches 1? Really, when we're taking the limit, we're just saying we're approaching this point, this limit, from both sides. So as the x from both sides, from the positive and the negative, so this is the left, which is net plus, and the right, which is minus, right? And we denote it as the limit as x approaches some number c plus or c minus in the superscript, right? It's not negative, it's just a notation we're saying from the left and from the right. And the idea is as we approach both of these from the left and from the right, our f of x, which is our y, is going to approach some real number. So in this case, if we get closer and closer to 1, we'll notice that our function will approach 1. So that's our limit. The limit as x approaches 1. of f of x, which in this case is x squared, is just equal to 1. So the absolute value of x over x, we have to realize that if we approach 0, sorry, because we're looking at the limit as x approaches 0. All right, limit as x approaches 0. Well, first we can look from the left, which is 0 minus of f of x. And look, as we get closer and closer, we're going to get to -1, right? This is just completely flat, so we are going to go to -1. But if we go from the right now, so the limit as x approaches 0 plus of f of x, which is from the right, we'll notice that we go to +1. But since these two limits don't equal, we say that the limit, the standard limit, does not exist. So does not exist, any. This happens when the side limits don't match, and there's some other cases as well. But the most important thing to realize is if the side limits don't match, then the limits does not exist. Now, over here is another example of where we have a limit that does not exist, which is this infinitely oscillating behavior. This is the graph of sine of 1 over x. At 0, I mean, you could tell it's going crazy up and down, which is known as oscillation. And really, there is no limit because the function doesn't actually approach anything. Graphically, you can tell this thing has no limit. So whenever there's an oscillating behavior in the graph, the limit does not exist. And finally, f of x is 1 over x. Since the function is unbounded at 0, right? We know that the limit does not exist. So we know that the limit as x approaches 0, 1 over x does not exist. Now, when we move on to infinite limits, we can talk a bit more about that. But for now, this limit does not exist because the function is unbounded. Topic 1.4 is estimating limit values from tables. So consider y is equal to x cubed. Now, this is the table of values. If we want to find the limit as x approaches 2 over x cubed, we have to take values of x closer and closer to 2. So notice, as we get closer and closer to 2, from the minus side, because remember, we're going from the left, values less than 2, our y's get closer and closer to about 8. And from the plus side, which is from the right, we're going, from the right of 2, we get closer and closer to 2. Our y values are also going to 8. So from both sides, our y is going to go to 8. So the limit is just going to be 8. This one, I wouldn't say it's too hard, but if we have that the side limits don't match right here, we have a different value than here, that's when we could say that the limit does not exist. Topic 1.5 is determining limits using algebraic properties. Right now, we're just going to look at the properties, then we'll solve some problems in a later topic. So, here are the properties or theorems that you need to know. The limit as x approaches c of a sum is the sum of the limits. We can factor out a constant for any limit. The product of two limits is just the product of the limits. The limit of a quotient is just the quotient of the limits, where remember, very important, the limit of the denominator cannot be 0. Otherwise, it's not true. If we have a power, so the limit as x approaches c of fx to the power of some number, that we could just take out the power and apply it to the whole limit. And remember, the power could be anything, so this also works for radicals, assuming that, it's defined and whatnot. And finally, for composition, which this one's super important, the limit as x approaches c of f of g of x is the limit as x approaches the limit as x approaches g of x of f of x. What this means is that this big limit can just be evaluated by first finding the limit as x approaches c of g of x, which is our input for f of x, and plugging that in for a limit as x approaches that number of f of x. And I'll go a bit more on that in just a minute. Topic 1.6, determining limits using algebraic manipulation. So for polynomials, you just have to plug in c into p of x. So p of x is the polynomial function. The limit as x approaches c of p of x is just p of c. Just plug it in, that's your value. For rational functions, um, you could just plug it in if possible, but if you get a zero in the denominator, then you should probably factor the numerator and the denominator, cancel whenever applicable, and after all that is done, then you could just plug it in. And if you have still a zero in the denominator, um, then that's an edge case, but you don't have to worry about that for now. Now, for radicals, you can just plug it in whenever it's possible because the limit of a radical is just plugging it in. But if you have it in, say, the denominator, you're going to have to multiply it by the conjugate. Now, topic 1.7 allows us to combine 1.5 and 1.6 and actually solve some limits. So for our first limit, we have a polynomial function. So what we're going to do is just plug it in. And you'll notice here, for the purpose of the AP exam, leave it like this, don't simplify. But since we're actually solving it, we're just going to get 2. Now for this one, we have a rational function. So what we're going to do is we're going to factor the numerator and the denominator. So first we can take out an x, and then we're left with, well, this becomes x squared minus x minus 30. And, you could do this algebra on your paper, but you're going to get x minus 6, x plus 5, whichever factoring method you prefer. And then the denominator, we could also factor an x. And when we factor it out, x squared plus 7x plus 10x, well, that is just x plus 5 times x plus 2. Our next step, if you remember from up here, cancel out where you can. The x's cancel out, the x plus 5 cancels out, and you just get the limit as x approaches 0 of x minus 6 over x plus 2. And finally, here's where, like I said, you just plug it in at the very end, minus 6 over 2 minus 3. Here we have we have a radical here in the denominator, and our first idea is going to be to plug it in, but if we plug it in, this becomes 0, this becomes 0, and we have a problem. So we have a 0 over 0, we can't do that. So we're going to first multiply by the conjugate of the denominator. If you remember what the conjugate is, well, then you should know that the conjugate of a plus b root c is just a minus b root c. You just change the sign. And this is going to be our conjugate. All of that divided by x minus 3 comes the square root of x plus 3. And when we actually work it out, we're going to get the limit as x approaches 9 of do not cancel out because why would we do that? We're just wasting our time. We literally just added it. So instead we're gonna do this, and it's getting a bit cramped here. But all of this will become x minus 9. Um, and in this case, like I was saying, the x minus 9s will cancel out. And I'm just gonna write it here. Now that the x minus 9s cancel out, we have now just a simple x plus 2 times the square root of x plus 3. Now we can just plug it in. We get 11 times 3 plus 3, 6. So we get 66. Finally, we're going to use a piecewise function. Whenever we have a piecewise function, the main idea is going to be to look at the boundary. So if we're evaluating it at an interior point, we don't have trouble. But if we're evaluating it, for example, at 4, which is where the function changes behavior, we're going to have to look at both sides. So from the left of 4 is actually going to be the same from the right of 4. This function doesn't make a distinguish. All it says is that x is not equal to 4, which is negative 4 to 4 union 4 to positive infinity. And this treating the left and the right as the same, so we can just say that this is going to be our limit, right? This is what the function behaves like at 4. Remember back to our limit definition, that's what it is, but we don't consider exactly at x equals 4 because that's not what the limit is. So we can actually just completely ignore this piece. Whenever you see x equals to 4, you can ignore it. You only have to look to the left and to the right, which in this case, we have both of these. Otherwise, we'd have to take side limits and check if they match. So in this case, we just have 8 minus 3 since the polynomial function, which is 5. So topic 1.8 is using the squeeze theorem to determine limits. Now, the squeeze theorem states that if h of x is less than or equal to f of x, which is less than or equal to g of x, in a neighborhood around C, which is basically saying in an interval containing C, but not necessarily at C, right? Um, That and the limit as x approaches C of h of x is equal to some real number L, or not actually necessarily a real number, as which is also equal to the limit as x approaches C of g of x. Then the limit as x approaches C of f of x is equal to L. So let me break it down. If f of x is bounded above by h of x and it's bounded above by g of x and bounded below by h of x, um, not necessarily everywhere, but at least in some interval containing C. And the limit of the lower bound, which is h of x, and which is equal to the limit of the upper function, right, the bound, g of x, if those two match, well then f of x is going to be squeezed between them, and its limit is also going to be the same number. So here is three functions, x squared times sine of 1 over x, and negative x squared. Now notice our f of x, which is the middle function, is getting squeezed between the two at 0. And the g of x and our h of x, both those limits of x approaches 0, that's easy to evaluate. It's the f of x that's harder. So how are we going to do this? First, we have to recognize the limit as x approaches 0 of our g of x, which is x squared, is just a polynomial, so it's 0. Same thing for h of x. That's also a polynomial, so it's going to be negative 0, which is 0. Since both of these limits match and f of x is being squeezed between the two, its limit is also going to be squeezed and it's going to be 0. So hopefully that made sense. And here's some common examples that you need to know. So this is the limit of sine of x over x as x approaches 0. This is equal to 1, very important. And the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. This one you can just derive from the first one. And here is an exercise which is to find this limit. So since we know these other two, we're going to first do tangent of x is sine of x over x cosine of x. And in this case, we're going to use our rules for limits to split this into sine of x over x times 1 over cosine of x. And for our leftmost, we know already this is 1 times cosine of 0 is 1, so 1 over 1 is also 1. So this limit is 1. So notice how we can use both of these to derive other limits, and this is all possible thanks to the squeeze theorem. Topic 1.9, it's not a big thing. It's just connecting multiple representations of limits. No new topics. We're just going to connect it. Back to the original problem I gave here in 1.7, we're going to have this f of x, which is a piecewise function. Here's the graph, here's the table, and here's just the algebra. So we already determined from up here that that limit is 5, right? Let's make sense to it though. Graphically speaking, notice although we have a hole here, we actually don't care what the function is defined as. We care about approaching it. So from the left, which is from the minus, notice how the function is going to go up to 5. And from the right, which is from the plus side, our function is going to go down to 5. So our limit graphically is going to be 5. So the limit as x approaches for f of x is 5, which is consistent with our algebraic answer. And finally, from the table of limits, as we go from the minus side, which is from the left of 4, our y's get closer and closer to 5. Also, as we go from the right of 4, our y's get closer and closer to 5. So our limit is also going to be 5. So this is how all three of these interpretations match up. Topic 1.10 explores discontinuities. So there are three types of them. Now, the first one is a removable discontinuity or a point discontinuity. And it's called that because it's only at a single point. Very similar to here, where we can just remove the discontinuity by filling in the point. It says that the limit exists, right? But it's not equal to the function's value. Now, this is only true if the side limits match. So if the side limits match, but they're not equal to the function's value, then it's discontinuous and has a removable discontinuity. We say f has a jump discontinuity if the side limits are not equal, so the limit does not exist, but the side limits are real, right? So what does this mean? The side limits are real numbers, right? They're finite, but they don't match from the left and to the right. And finally, f has an infinite slash essential discontinuity, which is a vertical asymptote if either side limit is plus or minus infinity. If the function is unbounded at some point, then it has an infinite discontinuity. So here are some examples. This is cosine of 1 over x squared. This is a very heavily oscillating behavior at x equals 0. I mean, it looks like it's just completely like paint, like blue paint, you just painted it over. That's how bad it oscillates. So in this case, we have a discontinuity. Now it's not a 1, it's not 2, it's not 3. I don't think there's a name as far as the AP exam goes. You just need to know that the limit does not exist, which we already learned, meaning that it has a discontinuity, but we'll get to that when we get to 1.11. So we have a discontinuity at 0. Here we have a discontinuity at 0 because the function grows unbounded at 0, meaning we have a vertical asymptote, right? Also, if we look at the side limits, here's where we get introduced to what it means to have infinite limits introduced, though. We get unbounded behavior, vertical asymptote, so it's not continuous. And finally, this is a special example. If you just look at the graph, we're only looking at -1 here. We have what's known as a gap or jump discontinuity because this jump is sizable. It's some sizable jump, but the side limit, so as we go to the left, we get one value. As we go to the from the right, we get one value, and those values don't match. So, topic 1.11 actually formally defines what continuity is. The Colligord says that a function f is continuous at x equals c, provided that f of c exists. That's condition number one. The limit as x approaches c of f of x exists, and the limit as x approaches c of f of x is equal to f of c. All of this is saying that the limit as x approaches c of f of x is just equal to plugging it in, evaluating it at that point, right? And really, the last condition is the only one that matters because we're just saying that, okay, f of c exists. C is in the domain of f. That one's pretty obvious if we're saying that these two are equal. The limit exists. Well, that one again implied if we're saying that these two are equal. And this is the main condition that we're going to be checking. Here's an important theorem to remember, although you don't need to know a name or anything, it's just a rule. That's that compositions, sums, differences, products, and quotients, of course, where the denominator is non-zero, of continuous functions at a point slash interval. We'll get to interval in just a minute. And they're all continuous in that point slash interval, respectively, meaning in that order. So if we compose or add or subtract or multiply or divide two continuous functions, we will get a continuous function. So here's an exercise. Given the following function g of x, is g continuous at x equals 2? So we're going to go to our definition of continuity. First, does f of c exist? Well, we're looking at 2, is f of 2 a real number? Yes, okay? We do have x is equal to 2, and that's 3. So f of 2 exists. Perfect. That's the first condition. Second condition, does the limit exist? Well, the limit as x approaches 2 of f of x, or sorry, of g of x, I should say this is g of x. So this limit is just equal to, well, we know that from the left and from the right, our function is going to be behaving like this top piece. So we're going to get the limit as x approaches to of x squared minus 4 over x minus 2, but we can factor this into x minus 2 and x plus 2. So then we can cancel out the x minus 2's, and we just get the limit as x approaches 2 of x plus 2, which is a polynomial, so it's just 4. So this limit does in fact exist, finally, this is the key thing. And when checking if the limit exists, we note that from the left and from the right, we have this single piece. Finally, is this limit equal to the function's output? Well, we already did all the heavy lifting in our first two conditions. Is 3 equal to 4? No. So g is not continuous at x equals 2. Topic 1.12 talks about continuity in an interval. And we define continuity in an interval by saying f of x is continuous in a comma b, which is non-inclusive, if f is continuous at every point in a comma b. But we say f of x is continuous in bracket a b comma b bracket, which is an inclusive interval, if f is continuous in a comma b, right? So it's continuous in every point in the interior, and the limit as x approaches a plus of f of x is equal to f of a, and the limit as x approaches b minus f of x is equal to f of b. The easiest way to interpret and understand this is a, this is b. We want to confirm continuity on this interval. So, of course, it has to be continuous at every point in the interval, but only at the ends, only at A and at B, we could consider from the right, which is plus, and from the left, which is minus. We don't care about what happens over here when we're talking about continuity in this closed interval. Now, it's very important to notice that polynomial, rational, power, exponential, logarithmic, and trigonometric functions are all continuous on all points of their domains. So they're continuous over their domains, right? Very important that you know this. So, for example, here's a question assessing understanding. So, show that e to the power of sine of 4x cubed minus 1 is continuous for all real numbers, right? In a set of real numbers by expressing it as a composition of two or more known functions. Well, this is actually just e to the x composed with sine of x composed with 4x cubed minus 1. If you see that, we're just doing this is our first composition, which is sine of 4x cubed minus 1, and we're taking e raised to that power. Now we know that first this is a polynomial function, so it's continuous. Sine of x is a trigonometric function, so it's continuous. And e to the power of x is an exponential function, so it's continuous. So all of these composed, which is our function that we're looking for, all of them are continuous in their domain. Topic 1.13 talks about removing discontinuities, and here's the problem straight from the AP exam. It's an older one, but so MCQs let f be the function defined above. It's a piecewise function. For what value of k is f continuous at x equals 2? How does this relate to removing discontinuities? Well, k is some value that we're trying to find, and the idea is that we're going to find some k such that this function is continuous. So previously, it's not necessarily continuous, it could be discontinuous. But we're trying to find some point, some value, sorry, especially if we're only looking at this original one, right? This one's more common. We just look at this, and then we're trying to remove the discontinuity by creating a piece, right? And this value of k, you should know, you have to know for the AP exam, that in order to remove a discontinuity at a point for a function, you have to redefine it, using these pieces as the original function when x is not equal to that number, in this case 2, and the limit of the function for x is actually equal to that. What does that mean? In order to be continuous, we want the limit as x approaches 2 of f of x to be equal to f of 2. And all of that should be equal to k since we know f of 2 is k. The limit as x approaches 2 of f of x is the following. But the x minus 2's cancel out, and we just have a polynomial function, so we'll plug it in and we'll get 5. Since we want this limit to be equal to k, which is 5, we want k to be equal to 5. So to remove this continuity, k should just be the limit as x approaches 2 of the original function, right? That's how we remove a discontinuity, by creating a piecewise function. Topic 1.14 connects infinite limits and vertical asymptotes. Here is where things can get kind of confusing between textbooks. So first we have 1 over x squared. Now, we talked about being unbounded, meaning that the limit does not exist. However, when you get to probably like, I would say real analysis, I don't know, calculus, different textbooks have different opinions on this. They say that this unbounded behavior, this idea of going up infinitely, it says that the limit is infinity. So first we have to look at the side limits. This is very important. Of 1 over x squared. Well, from the left, as we're going to the left, we're going up and we're going up, and we're going up infinitely. This is positive infinity. And the limit as x approaches 0 plus in a similar argument is also positive infinity. And since the side limits match, the standard limit is that. So for the purpose of the AP exam, don't get too confused. In this case, you can say it's completely valid to say that the limit is infinity, but not in the conventional way of what a limit means. Now, back to vertical asymptotes. Basically, we say that a function has a vertical asymptote at a point if either side limit goes to plus or minus infinity. In this case, both side limits go to plus or minus infinity. This is our f of x, which is 4x minus 3 over x minus 3. At x equals 3, f has a VA vertical asymptote because the side limit from the left is negative infinity and from the right is positive infinity. And you can notice this by kind of tracing out the graph, right? So we say that function has a vertical asymptote if the limit as x approaches c of f of x is plus or minus infinity, or actually any side limit. We could just say, well, the standard limit or any side limit. In this case, though, it is important to realize that all textbooks agree this is just completely true, that this limit does not exist. Because even if you consider infinity as a possible limit, neither of these side limits match. Topic 1.15 talks about end behavior in horizontal asymptotes and limits at infinity. So limits at infinity describe end behavior, and they're denoted as limit as x approaches plus or minus infinity of f of x. The key thing here to know is with rational functions. Now, this is just a big rational function, right? The numerator is a polynomial, the denominator is a polynomial. And the key thing to note is that the end behavior, which is the limit as x approaches plus or minus infinity, is determined solely by the leading terms, this ratio of the leading terms. Nothing else matters. I personally prefer this over memorizing, what to do if one is negative, the ratio of the leading coefficients and the powers, all that is truthfully a lot to memorize. And this is really the big thing that you need to know. Once you know this, everything becomes easy. So for example, we're going to solve the following limits. Remember, this is describing end behavior of the function. So end behavior to the right, which is positive infinity, is a rational function. So this just becomes the ratio of the leading terms. But we notice that this cancels out. So we just get the limit as x approaches infinity of 7 over 15x. What is that? Well, since we just have an x, that's just going to go to positive infinity, right? Another way to think of it is that this is the linear function, right, with a positive slope, so it's going to go to positive infinity. Here we have another rational function, so remember, only the ratio of the leading terms, 13x to the fourth over negative 7x to the fourth. These x to the fourths canceled out, and we're just left with negative 13 over 7, and that is our limit. So this is going to be a horizontal asymptote, right, which is at infinity. And here we do have another horizontal asymptote, believe it or not, but a very special one. So here specifically, um, notice that the degree of the numerator is less than the degree of the denominator. But wait, leading terms, this just becomes the limit of x approaches infinity of 1 over x to the fourth. But wait, the denominator is going to go to infinity, right? Or infinity to the fourth, which is just infinity. So it's 1 over infinity, but, that's just 0, right? So we say that it has a horizontal asymptote with y equals 0. That's the horizontal asymptote. And finally, we end off with topic 1.16, working with the intermediate value theorem, which is abbreviated as the IVT. Now, this is the statement. If f is continuous in bracket a comma b bracket and lambda or c or d, I don't know, and lambda is a number between f of a and f of b, then there exists some value c in the interval a comma b such that f of c is equal to lambda. In other words, this is more in explaining it. A continuous function takes all the values between f of a and f of b. It must attain every value there. Maybe this is a bit confusing, so let's break it down with an example. So f of x is x to the fourth minus 4x cubed minus x. Here's our graph. The idea is if we have any 2 points, right, here and here, let's say, and we know it's continuous. That's the first thing we have to establish. It's continuous, but it's a polynomial function, right? We know that. The key thing here to establish is that we're saying that between any two outputs of a continuous function, the function has to go through every output value between. So here's an application. Must there be some x in, actually, we could just say parentheses 1 comma 3, such that f of x is negative 10. How are we going to use this? Whenever they ask a problem like, must there be some time, must there be some input value in this interval, or must there be some input value such that the output is equal to this? You should probably be thinking, okay, how can I use the intermediate value theorem? And 90% of the time, the answer is going to be yes. Actually, probably 100% of the time, the answer is going to be yes, right? But the key thing is actually justifying it. So your answer should be yes and why. So your work should be first evaluating f of 1. F of 1 is negative 4, and evaluating f of 3, which is the other one, which is negative 30. And now from here, we need to have that lambda is a number between f of a and f of b. Is negative 10 between f of a and f of b? And the answer is yes, it is. Negative 10 is between negative 4 and negative 30. So by the intermediate value theorem, there is some number c in that interval, such that f of c is negative 10. And that is a full review of Unit 1, topics 1.1 to 1.16. Hopefully this helped, and good luck in studying for the AP exam.